All right, so in indicator 28, we're going to be comparing linear, quadratic, and exponential models. So this is kind of, I don't know, it takes in everything, a lot of what we have learned so far in Algebra 1. We spent a lot of time in linear equations, how to graph them, how to look at the different equations, how to go back and forth between the different forms of the equations as far as slope-intercept, standard, point slope, how to graph it with the y-intercept, what the slope means. Of course, that's going to come into play in this indicator. We spent some time in quadratics. Obviously, linear means line. When you graph it, it's a straight line. Quadratics graph in the shape of a parabola or a U, right? That's kind of the lazy way of saying it. And they can be positive or negative, which means they open up, they open down. Those are the only ones we get into in Algebra 1. As you go up into higher maths, you'll find quadratics that open sideways, but that's a whole different ball game, and that's way higher than what you get into in Algebra 1. And then exponentials, which we just finished last week, and of course exponentials, they grow or they decay, whichever way it's going, exponentially. Means it kind of starts out at a slow change, and then all of a sudden the change just ramps up really fast, okay? So in this indicator, we compare the three and we learn how to differentiate between the three, both in graphs, which is pretty easy because you just graph it and you look at it. Does it look like a straight line? Does it look like a quadratic, or does it look exponential? And then tomorrow we'll look into how to look at data from a table, and without graphing it, just being able to say whether or not it's linear, quadratic, or exponential, okay? So just as a quick intro, we're going to kind of compare the three. So first we're going to compare linear. Oops, no, we'll leave it red. Okay, so first we're going to look at linear, very basic. Okay, this is just a review. You guys know this. Linear is basically a straight line. So if you have a linear graph, it's going to look something like that. Okay, that's linear. And we've already talked about the way you get a straight line is because of that slope, that constant change, right? Once you have a slope of up something over something, that rise over run, you could put a bazillion points on this line, and they're always going to fall on the line because of that slope. Okay. The next one is quadratic. And a quadratic graph, okay, is a U shape, and it has a vertex or a point where it's kind of that center point. I should have done that a little offset so I could put the axis in there. But it has an axis of symmetry that runs right down the middle of the vertex. And what that axis does is it reflects. And that's why it made it easier to graph, because once we got a point on the left or the right, we could reflect it across that axis and get another point without having to do any math on the opposite side of the axis. So if you'll notice on these two, especially on linear, okay, if you have a y, this is our y-axis right here, right? On linear, are you going to have any repeating y's? Meaning, remember the whole, is it a function or not? Does it have any cheating x's, right? Any y's that repeat? Are you ever in linear going to have a repeating y? Because your y's go this way, right? So at this x, the y is down here at -2. At this x, the y is right here at 0. At this x, the y is at +1. And that y value is going to continue to rise. You're never going to have a repeat in y's. With quadratics, you do have a repeat in y's, because if you have a y over here, when you reflect it across that axis to find your third point, it's also going to be at the same y, okay? And so let me go ahead and write exponential, and then we'll talk about the tables and what they look like. So an exponential, our graph, okay. Oh, what happened to my blue? Oh, well, we'll do it green. Our exponentials started out slowly increasing and then shot up into the air really fast. And what these had is this imaginary boundary or asymptote that was part of the equation that stops it from going anywhere lower than that. And again, and we'll pull it up on Desmos and look at it, but you can't tell it by the human eye. You can't draw it with your pencil, but that green tail actually never touches, say that's -5. It never touches -5. It just continuously forever and ever and ever draws closer and closer and closer and closer to -5 without ever touching it. So it just kind of almost looks like it flattens out, but the head doesn't. The head shoots up and will grow exponentially fast, okay? That's called exponential growth. Will you have any repeating Y's? And when you were doing your exponential graphs last week, did you ever have a repeating Y? If you did, that meant you forgot to flip something, right? You forgot to flip a fraction, because you should not have any repeating Y's in an exponential, because it continually grows forever and ever, and it continues to decrease forever and ever. Although as you get closer and closer to that asymptote, those numbers get pretty tiny as far as the decrease, but they never stay the exact same, okay? So when you're looking at a table, try to squeeze it in here where I can still keep the titles on there. When you're looking at a table of these, right, your X and Y table, because anytime you have any kind of equation that has X's and Y's, you can always do an XY table, okay? With linear, your slope is what determines, right, your rise over run. So every time, let's say your X drops 1, 2, 3, or grows 1, 2, 3, your Y is going to change by the same number as well. So say this was a 2, 4, 6, right? So every time your X changed by 1, what happened to your Y? It changed by a +2 every single time, and it'll always change by a +2. So every time your X moves by 1, your Y in this particular table is always going to move by 2 because linear is constant. With quadratic, you should see an overlap. I have to make a little bit bigger T-chart here. With quadratics, when you get that center vertex, and we never really did a T-chart with quadratics because we didn't really need to, because we kind of cheated with our axis of symmetry and we gave ourselves that third point just by reflecting it. But had you put it in here, let's say the vertex was 2, 3, okay? If you go up 1 and down 1, what should the Y's do? Think about this on a graph, right? If you oops, I don't want that. I'll erase this in a second, but think about this on a graph. If you were to graph the vertex 2, 3, which would be about right here, and then I graphed the point 1, 5, right? So 1, 5 was here. If this is our axis of symmetry, how would we plot if this is 1, right? And this is 2, and this is 3. Where's the Y for 3 going to be? Somebody tell me. How do we find a third point? Noble? Yeah, we mirror it. So if it's on the one side, on this side of the axis, if it's at a height of 5, what's it going to be one side on this side of the axis? It's also going to be a height of 5. So if this is your vertex right here, or your axis of symmetry, then as you go one spot this way and one spot this way on your axis of symmetry, they're going to mirror, so they're going to be the same height. Now, we didn't have to put it in the table because we just did the mirroring, used the mirroring property to be able to graph that third point, but it always mirrors across that axis, which means your Y values are going to be mirroring each other through the table. So if I were to put the next one, let's say this is 0 and 4, right? And I said 10, what would 4 be? Would also be 10. It's always going to mirror across that axis of symmetry, okay? And it's kind of weird to look at it because when you're graphing it up and down, and your axis of symmetry reflects this way. But in a table, because you're writing up and down, your table should reflect around that axis of symmetry or around that vertex. So your Y's will repeat. So if you ever have repeating Y's in indicator 28, The only one it can be is quadratic, and that will come into play tomorrow, okay? And then with exponential, same thing. We did t-charts with exponential, so the t-chart idea should be or the XY table should be very familiar, right? And when you have 5 terms in your t-chart, which we got used to using, or at least starting with these, a lot of times you would start out with a little fraction, then it would get a little bit bigger, and then you'd go to a whole number, and then you'd start getting really big really quick, right? And it would start growing exponentially. Okay? So you'll notice the difference and we'll talk more about this part of it tomorrow, but you'll notice the difference in growth. As far as linear, you always have that very constant growth. Quadratic, you have the mirroring effect. And then in exponential, you have the change that gets, there's nothing constant about it. It gets bigger much quicker, okay? And again, we'll go into that a little bit more tomorrow. All right, the other thing I want to cover today, and I'm not going to really spend a whole lot of time on it, is plotting on a scatter plot, because you are going to do this in today's packet, okay? When you have a scatter plot, it's just simply a bunch of X and Y's, and you have an X and Y. Now, it looks a little different because we're used to seeing it extending into the negatives, right? And we're used to seeing it extending into the negatives this way. Now, I'll erase this, but this is our axis. This is our X. This is our axis. This is our Y. And the reason that it looks a little different is because in a scatter plot, unless your scatter plot has negative values, which I don't believe any of the ones that you have to work with do. No, everything's positive, so you don't need the negative quadrants. So you don't need over here, or over here, because those are quadrants that have negative values, and you won't be using them. So it looks a little different, but it is still an XY table. And the X and Y, this is still your X-axis, and the up and down is still your Y-axis. So when you're plotting points, right, you look at this first point here, and this point is 0.1, 20. So on the X-axis, you find 0.1, which you kind of have to sometimes look at your numbers and see if, I'll make this bigger, if that's 0.2, then this one would be 0.1. This one would be 0.3, right? This would be 0.5. Sometimes you're going to have to fill in the gaps because it's not going to number every single one of them for you. But that first point was negative 120. So at the negative 1x, you would go up to the 20 and you would plot the point. Then you would graph negative 130. Or negative 1.130. Then 0.230. Then 0.240. 0.340. 0.450, 0.670. Did I skip one? Nope, 0.670. When I'm actually doing this, if I were doing this as homework, every time I graphed one, I'd kind of put a little check mark next to it so you don't lose a point. 0.770. Now, this is data, right? This is not a T-chart for one line. This is data. So we're looking at the model of data, okay? And that's where kind of the new terminology comes in. Let's see, 0.77, 0.77, don't have to graph that twice, and then 0.88. All right, if you're looking at the model and you're guessing between linear, quadratic, and exponential, does this data tend to trend, okay, it's not exact, but does it tend to trend linear, quadratic, or exponential? Meaning, right, does it look more like the model? Does it look more like a straight line? Does it look like it's trending in a U, or does it look like it started out flat and then exploded really high in the air? So with scatter plots, you use the idea of the shapes that they create, but you don't worry about the whole no repeating X's and Y's, okay? So in this shape, you look at this model and you can see that it's trending in a straight line up, and so this would be considered a linear scatter plot, okay? I'm not going to take the time to graph the other two. What I will do real quickly is, let me save this answer key and shoot it over to my other computer so I can show you already graphed. I think that'll be quicker here. Just the assignment, or just the answer. There we go. So if I go back here, I want to just show you what they look like once you get all those plots graphed. No, come on. It needs to pop in there. There it is. So when I graph, if I were to graph the other two that I had on there, and I just want to show you what they look like when you graph all the points here. All right, so you can see that in that first one, right, all the points I just graphed, you can see that it looks like the ones I graphed. And then again, if you were to draw just a line that kind of held the shape of the points, it's not going to go through every single point because obviously every single point on a scatter plot doesn't line up perfectly. But if you were to draw basically it's called a line of best fit, but if you were to draw the best shape you could through that, it would go linear, okay, which is why that would be considered a linear graph. You look at your data points from that second one, and if I had plotted all of them, this is the shape it would have taken. That's all those data points plotted, and you can see that they take the shape of a quadratic, okay? Not every single one of them is going to fall exactly on that, but that's the basic shape. And then this is an example of an exponential data points, right, where you've got a bunch of them lined really, really close to a certain line, a certain asymptote, which in this case is 0. And then you can see that there is definitely a few points that shoot really high up into the air. So on your packet today, you're going to be graphing points just like this, and then you're going to be deciding, does it look more linear, quadratic, or exponential? And what you have to be careful with, and I don't know if any of yours will look like this, but if sometimes you'll have points that do something like this. So you'll have a few here, and then maybe a couple here. Even though some of them are off the graph, and if you were to continue your quadratic, they would be over here in kind of this no man's land, you have to visualize that this part of it right here still is quadratic, even though you're missing half of it, okay? It's not exponential unless there is a definite flattening. And so for this one right here to be exponential, you would not have these points right here because they definitely trend back down. If it's exponential, you're definitely going to see a flattening, okay? So that's how you can really tell the difference between quadratic and exponential. Even if it goes off your graph a little bit, quadratic is definitely going to have that bend back the other way, whereas exponential won't, okay? I think that pretty much the only other thing I want to cover as far as your packet today is it talks about, okay, it'll give you some scatter points. So it'll give you an XY table, and it'll say like age and height or something like that. Okay, it'll be some data. It'll give you the X's and Y's. X's are always on this side, even though they don't say X and Y. X's are always on that side of the point. Then it's going to give you what it looks like graphed. Okay, so let's say here those are your points. So then it's going to give you this. And then it's going to tell you that it's modeled. This is how it's going to be worded. It's going to say that it is modeled by, and then it's going to give you an equation. So like here, it might say y equals 2x squared plus 3x plus 4. Well, that's obviously a quadratic equation. The graph is a quadratic. And then it's going to ask you questions, okay? And it's going to say based on the model or using the model. When it says that, this right here is what it's asking you to use. It's wanting specific answers. It's not wanting you to look at the graph and estimate. If it wants you to estimate, it will tell you, estimate what it would be at a certain age or at a certain height, where you have to look at the XY chart or the X's and the Y's, right? And you got to look and see, okay, if it were here, if I'm going to estimate my Y, it would be about there. Okay, that's an estimate. That's using the graph. When it says according to the model or using the model, it wants you to use the equation. So if it tells you that, say, the X is age and the Y is height, and then it gives you, so let me write that down. So if it says X is age and it tells you Y is height, right? And then it says, according to the model, what height is this person expected to be at age 27? Where would I plug 27s into the equation? I would plug them in everywhere I see an X. And then I would solve for Y, the height. Vice versa, if it says if a person is the height of 5 feet, at what age would they reach that? Well, that's your Y, because your Y equals height. So in that instance, you would plug a 5 in where there's a Y, and then you would solve for your X's. Okay? So when it's asking you according to the model, it means according to the equation that they provide for you. Okay? Now, I want you to kind of plod your way through the packet at first. You may not know how to answer every single one of them. A lot of it is trying to use common sense and using rational, like deciding, okay, if the X means this and the Y means this, what does it mean? What does the Y-intercept mean? Well, the Y-intercept means that, it's at that 0x. And so what does that mean? Is that age? Is that height? Is that distance? Whatever the X equals. So you kind of have to be able to look at graphs and start deciphering what they mean a little bit, okay? For those of you at home, click load, work through the packet, and then we will go over that packet again via video, and I'll post that later on, okay? Email me if you have any questions.